So, yeah. Okay, so I'm going to be giving a series of lectures and on the non-abelian Hodge correspondence. And so today I would like to just start sort of in an introductory way by introducing the characters. And so there are, roughly speaking, two big branches here. One comes from the harmonic map theory. The second one comes from Higgs bundles. So I'll just briefly introduce these two. These are big topics, but I'll just talk about very, very essential points in both of these things that I want to explain as the lectures go on. And then, of course, the correspondence between the two. And maybe I'll also mention some applications. And then I'll outline the plan of the rest of the week. Okay, so let me start with, right off the bat, with harmonic maps. So let's let X and N be Riemannian manifolds to start with. So if I look at maps between these two manifolds, then I can define the energy to be the integral over X of the norm squared of the derivative. So here, the derivative of this map is an element of the, is a one form on X with values in the pullback of the tangent bundle on N. And I have Riemannian metrics in both cases, and so I use those Riemannian metrics to define the pointwise norm of the derivative. And then I integrate that over the manifold X with respect to its volume form. So this is the energy functional. And a harmonic map, roughly speaking, is a minimizer of the energy. Or maybe it's just a local minimizer of the energy, so it should be a critical point of this functional. So definition. So a C2 map is harmonic if it is a critical point for the energy. So we can write down the Euler-Lagrange equations, and we see that we get, in invariant notation, it's this simple form here. So what is gamma? Gamma is the Levi-Civita connection on N. So as I mentioned over here, du lives in the pullback of the tangent bundle, and it's a one form, so I want to take the adjoint of the de Rham operator here, but I need a connection on this bundle to do that, and so I use the pullback of the Levi-Civita connection on N to do that. Okay, so this is invariant notation, but maybe one should see what this looks like in coordinates. So in local coordinates on N, so then these equations are the same as taking the Laplacian of the coordinate functions plus the Christoffel symbols. So one can work this out. So the gradient of uj dotted with the gradient of uk. So this dot product is using the metric on the domain. Okay, so these are the local equation. All right, so what are some examples? So the easiest one is when n is just Euclidean space. And then the coordinate functions, I can choose global. This depends on both metrics. This depends on the metric on the target. And the star, that's right. This also depends, that's right. This depends on the metric on x, right through the Hodge star there. Depends on the metric on the target through the connection, and the metric on x through that. Right, so when we have global coordinates, then the UIs are just harmonic functions. What's another example? So I'm choosing my examples carefully to be relevant to the rest of the talks. So if I take Kaehler manifolds, when both the domain and the target are Kaehler, then holomorphic and anti-holomorphic maps are both harmonic. Okay, so we'll see this later on as well. Another example that's relevant to what we're going to be doing is the following. So suppose I take a slight variation on this. So suppose I take a cohomology class, and the first cohomology, let's say with real coefficients on x. So I can think of this, right, as hom of h1 of x into R. And I can think of this as hom, if I like, of pi1 of x into the isometry group of R. Actually, just the translations on R. Okay, so I can think of this as giving me a representation of the fundamental group into the isometry group of my target, which is just R in this case. All right. So here, what I'm going to look for is not a harmonic map from X, but a harmonic map from the universal cover of X that's equivariant with respect to the representation. Okay. So, and this is coming from this choice of cohomology class here. So it's not hard to write down what this is. So I can just choose a base point. And then I can just let u of p be the integral of this representative here. Alpha is a closed form representing this cohomology class. And then this will, by definition, be equivariant with respect to the periods of this cohomology class. Okay, so if I change P by a deck transformation on the universal cover, then this map translates exactly by that period, that corresponding period associated to alpha. So this is an equivariant map in that sense. And what is the derivative of u? It's just alpha. And to say that u is harmonic, that's if and only if the star of alpha is 0, i.e. alpha is a harmonic one. Okay, so this is a very relevant example for us. And then the last example, I'll try not to block it here, is when the domain X is a Riemann surface. So here, let me point out something, and this is what Indrano was foreshadowing, I think, is that in this case, the energy is actually conformally invariant. That's a manifestation of two dimensions. So if I think about that, the volume form involves the metric, the determinant of the metric in local coordinates. And I'm contracting using that metric to contract here. So the scale is exactly the same. So here I'm scaling the metric, and so that scales the determinant by by the square, but then the volume form is the square root of that. So this scales like, the volume form scales like the metric scales. And on the other hand, I'm contracting by the metric. So that's an inverse metric here. So scaling the metric does not change this integrand, and so therefore it doesn't change the energy. And sure enough, these coordinates are conformally invariant as well. If I scale the Laplacian, if I scale the metric, I just scale the Laplacian, and I'm just scaling the gradients by the same thing. Okay, so in any case, the upshot is that harmonic metrics from harmonic maps from Riemann surfaces only depend on the Riemann surface structure. They don't depend on the volume form of the domain. Okay, so in that case, there's a very interesting quantity that appears. So if this is a harmonic map, then I can pull back the metric from N and view this as a symmetric two-tensor in the complexified tangent bundle, cotangent bundle. So I can take its 2-0 part. So more concretely, what I'm saying is I can take du, I can take the 1-0 part, because I have a Riemann surface structure, and I can take the inner product. So this is a pullback tangent bundle, so I can take the inner product with respect to that metric there. So this is called the Hopf differential. So it's a quadratic differential on the Riemann surface. Unfortunately, there's something else called the Hopf differential, so one has to be a little bit careful about the terminology. But the upshot here is that if U is harmonic, then this guy is holomorphic. And this is holomorphic. Okay, so that's an easy calculation to do just using this definition that I've done here in the local expression. Okay, so what we see is that in the case where we have a Riemann surface, then what appears from harmonic maps naturally is a holomorphic quadratic differential. And this is a phenomenon that we're going to see in higher dimensions as well. Okay? All right. So those are some simple examples of harmonic map. And so let me just state the main classical theorem about harmonic maps, because that's going to be relevant to us. So unfortunately, I just erased the equation, but in any case, what we see from the expression in local coordinates is that the harmonic map equation is a nonlinear equation. Mildly nonlinear. The high order term just looks like the Laplace operator, and then we have nonlinearity in the first order terms. But in any case, one might expect that there's energy concentration. There could be singularities in harmonic maps. And so that's the general thing that one can expect, unless there are curvature assumptions. So this was probably first formulated by Eels and Simpson. So it's called the Eels-Sampson-Bochner formula. So let me say, suppose I have again a harmonic map in the way that I formulated it, and so then the Bochner formula has to do with this energy density. So it says the following: so the gradient of the energy density, the Laplacian of the energy density, is just the gradient of du plus a term involving the Ricci curvature on the domain, and then minus a term that involves actually the sectional curvature on the target. Okay, so I'm not writing out the details. You can do this by choosing local frames or something, but here this is the sectional curvature on N, and this is the Riemannian, this is the Ricci on the domain. Okay, that's the form of the terms. And the key thing here is this minus sign. So it turns out this minus sign is important And of course, then I have to tell you which Laplacian I'm using. I think I'm using the analyst Laplacian. So, okay, in any case, so the sign here matters. And what this tells you, so what this tells you is that, you see, so this term is quadratic. This term is quadratic in du squared. It's fourth order in du, so it's quadratic in du squared, roughly. And that can cause real problems. You'd be saying the Laplacian of a function is some constant times the square of that function, and so you can see that you can have problems with the regularity of a weak solution of that equation. Unless the sectional curvature of the target is negative, so that this term is actually positive. Okay, so when the sectional curvature of n is non-positive, then that implies that that if we forget all the other terms here, forget that term, that's positive, that term now is positive, this is just some possibly negative constant times du squared. And now this is a very nice equation. Okay, so now it follows from a standard fact that the sup norm of du squared is bounded by the L1 norm. And this is just the energy. And plus there's a parabolic version of this, which I will use tomorrow. Okay, but here I just want to give you the general idea is that in the presence of non-positive curvature, then you get nice bounds on the, you get Lipschitz bounds in the map that are just uniform in the energy of the map. And this leads to all sorts of very, very nice properties that just simply don't hold if you drop that assumption. Okay, so what is a consequence of this? A consequence is an existence theorem. So let me just state that theorem. This is the theorem of Yields and Simpson. Is that suppose that X and N now are compact, then in every homotopy class, of maps U from X, there's a harmonic map. And the map is essentially unique. One can be precise about when it's not unique and exactly how it's not unique. So in particular, if n has strictly negative sectional curvature, then the map is unique. Okay, so plus some uniqueness under assumptions, under additional assumptions. Okay, so there exist harmonic maps. All right. So what we're interested in is in Kaehler manifolds. So let's see what the harmonic map equation looks like in the Kaehler case. Oops, I shouldn't have erased that. That's a very good point. So that's right. That's right. So So let me say this again. So in the case of negative sectional, so let me just make a more precise statement than I just did. So in the case of negative sectional curvature, the statement is that either the map is unique or it maps onto a geodesic, and points are considered geodesics. If it maps onto a geodesic, it's not going to be unique because you can move it around on the geodesic. And that's the only thing that can happen in strictly negative curvature. More generally, if you have flats, then you can translate along the flats, that sort of thing. Other questions? Yes? I'm sorry. So, yes, N has non-positive sectional curvature. So I was explaining as a consequence of that, and I forgot to write it down as a hypothesis. You're absolutely right. So this works for N having non-positive curvature, and if you drop that assumption, then there are examples where it simply fails. You do not have harmonic maps on every homomorphic class. Okay, so what happens in the case of Kaehler manifolds? So higher dimensional Kaehler manifolds. So now let's if X is Kaehler, so recall the equation that I wrote down here, the condition for harmonic map. So d gamma, so this is essentially d gamma of star of du. Okay, and now on a Kaehler manifold, so omega is the Kaehler form, and J, say, is the almost complex structure. Then star of du, there's another star, but I think it's, I can just take star. It's an isomorphism. So 0 is okay. Since it's 0, it doesn't matter. So here, up to some constant that I'm not going to worry about here, this can be written as omega to the n minus 1 wedge j of du. And now we're on a Kaehler manifold, so d of omega is 0. So here, let me call this dc by definition. So in local coordinates, this looks like d bar minus d, the round del minus del, rather. And so omega is 0, so when I take the derivative, it passes through that. And so the harmonic map equations on a Kaehler manifold just become omega to the n minus 1, wedge ddc of u is 0. So there's a natural special case of this, and that's where this term is already 0. So the definition is U is pluriharmonic if this term is already 0. So this is equivalent to saying that, see, this is sort of the two-dimensional kind of portion of the derivative. This is essentially dd bar of u in local coordinates. And so this is saying that u is harmonic. So let me state this correctly. So the restriction of u, this is if and only if the restriction of u to every germ of a complex curve is harmonic. So it's harmonic in all the complex directions. So this is an extra condition, and And it's not something that one would expect to be true. So this is somehow, in some sense, this is overdetermined, is what I want to say, in higher dimensions. And so one would not expect harmonic maps, for example, to always be pluriharmonic unless there's something rather special going on. And so non-positive curvature, in other words, turns out not to be quite enough. And so Hsu found exactly the right condition. So here's a definition. So again, N is just a Riemannian manifold here. And we'll say that it has a non-positive complexified or Hermitian, sometimes it's called Hermitian, sectional curvature. If whenever I take the usual sectional curvature, and here, don't take any of my signs seriously. So whatever the right form of the sectional curvature is in the normal case, to say that it's non-positive, you would say this for just tangent vectors, and the notion of complexified sectional curvature is just do the same thing where you feed in complexified tangent vectors, where you just extend the Riemann curvature and the metric complex linearly. Okay, so X and Y are in the complexified tangent bundle. Okay, so this implies, in particular when you take real X and Y, of course this implies non-positive sectional curvature, but it turns out to be a stronger condition in general. So this is then non-positive curvature. But the main examples for us are when N is a locally symmetric space of noncompact type. Okay, so these will be the relevant target manifolds for harmonic maps in the non-abelian Hodge correspondence, and those manifolds always have non-positive complexified sectional curvature. Okay, so then what is the theorem? The theorem is due to Hsu and Simpson. So just a little bit of the history. So Hsu introduced this notion when N was a Kaehler manifold, and Simpson noticed that you didn't really need Kaehler to have an interesting extra condition. Just the Riemannian case is enough, and so that's where this comes from. And so here, if N has non-positive, maybe I should give this a name. I'll call this. So NPC normally means non-positive sectional curvature, so I'll call this NPHC, non-positive Hermitian sectional curvature. So if N is NPHC, and again here, just to be on the safe side for now, let me state the theorem when I'm assuming both are compact, although it's going to hold in much more generality there. Then the statement is, No, it's not bisectional curvature. It's, yeah. Something different. So if x and n are compact, then, and x is Kaehler, then harmonic maps from U to N are pluriharmonic. So this extra sort of rigidity property here holds for harmonic maps in the case where you have non-positive Hermitian curvature. So this is actually a key thing in the non-abelian Hodge correspondence. So I will actually prove this tomorrow if I'm on schedule. In the case that's relevant for us, we'll prove this tomorrow. Yeah, so again, the locally symmetric of non-compact type. That's the only example that I'm going to be thinking about. So I thought you were going to ask, do you have an example of something that's non-positive sectional curvature but not non-positive complexified? And I was trying to think of an example. There must be an obvious one. I just couldn't come up with it before today. But these examples do exist. So this is definitely a stronger condition. Okay. Other questions? Okay, so that was the very, very brief introduction to harmonic maps. And so now let's talk about Higgs bundles. Okay, so let's let E be a Hermitian rank n vector bundle on X. And so I'll let GE be the bundle of skew Hermitian endomorphisms. Okay. And so given a unitary connection, A on E, so I don't know, I use A for the name, but then dA for the corresponding derivatives, so the notation is maybe not the best. But so given a unitary connection, so one that preserves the Hermitian structure on E, and an element psi, which is just a one form on X with values in the Hermitian endomorphism bundle, so square root of minus 1 times E. So this is sometimes called the Higgs field. So then we can write down some natural equations. I don't know if they're natural or not, but in some sense, to a physicist, they would be rather natural equations, namely the curvature plus the bracket of psi, and then d psi equals 0, and dh psi equals 0. So here, if I took the L2 norm squared and summed up all of these terms on the left-hand side, then that would be the sort of Lagrangian that a physicist might actually be interested in looking at. And these would be particular classical solutions, namely the absolute minimum solutions for that Lagrangian. Okay, so these are natural equations in that sense. And so what do I want to say about these? So if I divide up these equations in sort of two pieces, so I can look at the first two equations, or I can look at the second two equations. And here, let's continue to assume, this makes perfect sense on any Riemann manifold, but let's assume that X is Kaehler. So then the first two equations are nothing but flatness equations. Not of the unitary connection, but of the connection that's built out of adding to the unitary connection a Hermitian piece from psi. Okay, so if I just square this term and divide up into Hermitian and skew Hermitian pieces, then I get these two equations from the statement that Nabla is a flat connection. Okay, and if I look at these two equations, this is holomorphicity. Of phi. And what is phi? So here I can write psi. Since I'm on a Kaehler manifold, I can write psi in terms of it's 1, 0, and 0, 1 parts. So this is saying that this one form with values in the endomorphism bundle, this one form is harmonic, and when you take so if I take the real and imaginary parts of this holomorphic guy, that's psi, and so real and imaginary of holomorphic is harmonic. Okay, and so now there's an extra condition here, and that is that of course, so this would be saying that phi i.e. phi is a holomorphic one form with values in the endomorphism bundle of E, but we like the endomorphism bundle of, this makes sense as long as the endomorphism bundle of E is actually a holomorphic bundle, so we'd like this, in other words, we'd like this d-bar operator here to be integrable. And so integrability of d-bar A is the same thing as saying that the 0, 2 or 2, 0 part of the curvature is 0. And if we go back to these equations and look at that, that implies something more about phi, namely that the bracket of phi with itself is 0. Okay. So this, we will see, is a manifestation of the Simpson theorem that I was talking about just a few minutes ago. So I'll try to explain this tomorrow. Okay, so this kind of motivates the definition. Of a Higgs bundle. So a Higgs bundle on X is a pair E, P. So E is a holomorphic bundle. Phi is a holomorphic one form with values in the endomorphisms of E. So holomorphic with respect to that holomorphic structure, and the additional equation that the bracket of P with itself. Okay. So this is what we mean by a Higgs bundle on X. Okay, and so it turns out that just like in the difference between pluriharmonic and harmonic, these equations are a little bit too strong. These are overdetermined, and so there's another set of equations that are more natural in this context. So, so let's let lambda be the dual of the Lefschetz operator. On X, so i.e. contraction with the Kaehler form. Then we're going to replace that first equation by this one. And here I'm going to put a -1 here. And possibly a constant times the identity. Where mu is a constant. Okay, so here I'm not going to require this to be 0, first of all. Mu doesn't necessarily have to be 0. I'm not going to require what's inside here to be 0. I'm not going to even require anything about the other components of this other than the ones that are in the direction of the Kaehler form. Okay? So this is the more natural equation, and maybe I'll explain this maybe on Wednesday, is that this is a more reasonable equation. Namely, if you think of this as some nonlinear PDE, then the highest order term is a Laplacian. So it's a sensible, non-overdetermined equation. So this is, in the case where you turn the Higgs field off, this would be called the Hermitian-Einstein condition. And so, or Hermitian-Yang-Mills. And so maybe I'll call this Higgs Hermitian-Yang-Mills. Okay, so those are the equations that we're going to be interested in here. Let's see, how am I doing on time? Okay, and so now the question is the following. So I started out by saying these are natural equations, and then we abstracted the notion of the Higgs bundle. So now the question is, given a Higgs bundle, is there a metric where these equations are satisfied? So I can view these equations as an equation. Where does the metric appear? It appears here, because this is the curvature. I didn't say that, but this is the curvature A, is the Chern connection. On E. So I have a holomorphic bundle. If I choose a Hermitian metric, there's a uniquely determined connection that's compatible with both the holomorphic structure and that metric structure. So that's what I'm calling A here. So the metric appears in there, and it also, of course, appears here in the in taking the dual of the Higgs field. So one can view this as an equation on the metric, in other words, this condition. Given a fixed Higgs field, this is some equation on the metric, and in fact, as I said, it's a nonlinear PDE in the metric. The leading order term is like the Laplacian. So it's some interesting nonlinear PDE that sort of is like the harmonic map equation in some sense. Okay, so it's very closely related. Okay, so we can ask when can we find a metric that satisfies this for the Higgs bundle, and it turns out that you can't always do it. And so I will talk about that later. So it turns out that we might not be able to find satisfying the Hermitian-Yang-Mills equation. Okay? And in fact, one can see immediately that a solution to the equations implies a condition on subsheaves. So this leads to the notion of stability. So let me define stability, and then I think I can state the main theorems after that. Okay, so here's a definition. So again, X is a Kaehler manifold, and I've got a Higgs bundle. So intermediary F here is a torsion, if F is a torsion-free sheet. Then the degree of F is just the integral of the Chern class against the Kaehler form. And the slope, this is called the slope, is the degree divided by the rank. And so then stability has to do with the slopes of subsheaves of the Higgs bundle. So E phi is stable if for all subsheaves F, where the rank is strictly between the rank of E and 0. And an extra condition here is that, so I can think of phi as a holomorphic one form with values in the endomorphism bundle. And so I require that when I map this subsheaf here, this lands in the subsheaf again. So this is in the holomorphic tangent bundle. How should I call that? Let me do it. Stay with the sheaf theoretic. Unfortunately, I use too many. So omega, unfortunately, I use too many omegas here. So this is the sheaf of, this the holomorphic cotangent bundle. So this is sometimes called invariant. So if I look at all subsheafs that are invariant and are not E, don't have the same rank as E, then I want the slope of F to be strictly less than the slope of E. Okay. So this is the definition of stability, and then there are variants on this. Semi-stability is where I allow an inequality like this, and polystability means direct sum of stable with the same slope. Yes. That's right. Okay. And so then where does this definition come from? Well, it comes from staring at that equation and seeing what that equation implies. And so that will be the something that I'll do probably on Wednesday is as we shall see, that the Hermitian-Yang-Mills equations implies that E is polystable. Okay, and so this maybe is, I should give attributions to things. This is essentially goes all the way back to Lütke. Okay, and so that's automatically a restriction on the types of Higgs bundles where you might expect a solution to this kind of PDE. Okay, so so I've set things up, and I think I have 5 more minutes at least. We started a bit late, right? Okay. So now let me state the main theorems, and then this will be the topic of this week. First of all, any more questions on this? Okay. So here are the main theorems. So the first one has to do with harmonic maps. And so this is Corlet's theorem. And I should say that behind each of these, there are many other people, of course, involved. So this theorem is a sort of generalization, sort of comes on the heels of earlier work of Diederich and Savoie, Donaldson, and then later Labourie and Yosten Yao. Just to give some names there. So the theorem is the following. So let's let X be just a Riemannian manifold, compact Riemannian manifold. And let's let rho be a representation of pi 1 into SLNC. Okay, so of course, there's a much more general theorem here, but let me just stick with the case that's relevant for us. Then, and also let N be the symmetric space of noncompact type. Then the theorem is that there exists a rho equivariant harmonic map from the universal cover of X to N if and only if rho is semi-simple. And moreover, if X is a Kaehler manifold, this map is pluriharmonic. So that's the Sue-Sampson result. If X is Kaehler, then U is pluriharmonic. Okay, so that's the sort of harmonic maps side of this whole story that is going to be relevant for us. As I say, there's a much more general result that has to do with representations into reductive Lie groups. Maybe I just won't state that theorem. This is all we'll need. Okay, so I will essentially give a complete proof of this tomorrow. It's not that difficult. Okay, so the second side of the story is which is a theorem of Hitchin originally, and then Simpson more generally. And of course, this is in the line of results that go back to really Narasimhan and Seshadri. Donaldson, and Uhlenbeck, yeah. And this has to do with solutions to the Hitchin, the Hermitian-Yang-Mills equations. So let's let X be a compact Kaehler. And E a Higgs bundle. Then there exists a metric, a Hermitian metric, satisfying the Hermitian-Yang-Mills equations if and only if E is polystable. And now there's a moreover as well over here, which I haven't talked about yet. So remember that we don't really want these equations. We want the equation that says that this is 0 before doing the contraction, because that's the one that's related to flat connections, and that's the one that's going to link up with the left-hand side of the board. And so there should be a kind of rigidity phenomenon like over here that tells us when that's the case. And here it's rather simple. So moreover, if I look at the Chern numbers of E, so here this is just involving C1 and C2. If these two vanish, then in fact the stronger condition is satisfied. Okay, so this is kind of the second side of the board. I guess I got my orders backwards. No, I got them correct, right? Started out by talking about harmonic maps, and there's the harmonic map theorem. Higgs bundles is on this side. And now, of course, you see that there's a relationship between the two, and that's the non-abelian Hodge correspondence. So we've sort of already seen it because I introduced these equations by noting that they give us naturally flat connections. And so I just have to sort of explain how to go from the harmonic map side to the solution to the Hermitian-Yang-Mills equations as well. Okay, so this is the non-abelian Hodge correspondence saying that these two problems are sort of related. And so let me phrase it in the following way. So again, let's say X is a Kaehler compact Kaehler manifold. Then so M Betty, so this is for SLN-C, say, is homeomorphic to the moduli space of Higgs bundles of rank n and vanishing Chern numbers. I don't know how to write that. C1. Let me say C1 is 0 and C2 is equal to 0. So this condition here is what I actually need. Okay? So what are these spaces? So this is the Betty moduli space. So this is just homomorphisms of the fundamental group into SLN. And then you take the geometric invariant theory quotient by the action of conjugation on the representations. Yes. I didn't mention that. That's a very good point. So for these Higgs bundles that I'm talking about here, if I really want to talk about SLNC, I should fix the determinant of E to be trivial, and the Higgs field should be traceless. Thank you. And so this guy here is the moduli space of solutions to these equations. If X is projective, then this is a quasi-projective variety. So let me just say this is the coarse moduli space. Of semi-stable Higgs bundles. Satisfying all these conditions that we talked about. And then this correspondence as a homeomorphism. Okay, so these are both, as I say, what X is a projective variety. These are both algebraic varieties. I guess what X is Kaehler, this is a complex analytic space. But those complex structures are different. Okay, they're actually very different. So this is a homeomorphism, and so this is the non-abelian Hodge correspondence, and we'll see that I guess I've sort of run out of time here, but this actually has rather important applications to Kaehler groups, for example, and so. Maybe I'll state some of those if I have time later on. And I think that Lauer's going to tell you a little bit more about the structure of this space in the case where the underlying manifold is a Riemann surface. This has an extremely rich structure. And then maybe later on in the week I'll come back to the Riemann surface case and try to say something more about how that blends in with the harmonic map picture that we had before. But in any case, this is the theorem, and so the plan for the rest of the week then is so the plan is so tomorrow I would like to prove Corlet's theorem. And as I say, that involves the Sue-Sampson theorem as well. And then maybe on Wednesday, I'll do the Hitchin Simpson. So here, I'll be less complete. It would take me way longer than one lecture to try to really even get close to this, but I'll just try to give some ideas of the proof. And the ideas that I will give are particularly relevant to extra structure that comes up here, namely the action of C star, which is also very relevant to this whole picture. And so this will be rather sketchy. And then maybe, as I say, later on in the week, if I have time, I'll talk about harmonic maps to trees. And the relationship with the spectral curve picture that Laura is going to be lecturing on starting this afternoon. Okay, so I apologize for going over, and we'll continue tomorrow. Yeah, so that's very good. You just, yeah, I was trying to be a little bit too simplistic here. Yes, absolutely. So strictly speaking, right. So strictly speaking, when one constructs this moduli space, you want to use Giesecke stability. So let me just think here 1 second. So the statement of this theorem, as I stated, is correct. Over here in the construction of this moduli space, as Johan points out, we really should use more like a Gieseker type stability. For E. So let me address this next time. I think the statement that I've stated here is correct as it stands, but I should just clarify that a little bit.